Congratulations, you have made it to the end of Chapter 7. This is the last section in the textbook, Section 7.3, where you've learned what the exponential equation looks like, you've learned how to graph them, and I guess the last thing we need to do is learn how to solve them. I'm going to show this to you in two different ways, okay? You're going to learn a way where you can do it kind of using algebraic techniques, and of course, if that all doesn't work, then I'm going to show you a graphical technique. So if you got your graphing calculators, bring them out, you're going to use them, okay? But before we begin, when we're solving exponential equations, it's nice to know your exponents, especially the perfect squares, cubes, power 4s, 5s, and maybe 6, okay? So to complete the chart below, I hope you can do these without the calculator. But if you can't, then I'm going to ask you to use your calculator to figure it out. I think you should memorize all these, okay? If you have them memorized, it's much easier. If you don't have memorized, well, it'll be much harder, okay? 2 squared, yeah, that's 4. 9, 16, 25, 36, 49, 64, 81, 100. I know there should be a few more, but at least know these 10, okay? Cubes you should know too. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 times 6 is 36 times another 6. I believe that's 216. 7 cubed, 49 times 7. How about 343? 8 cubed, 64 times 8. I think that's 512. If you want to do 9 and 10, you could do that too. I think that's 729, and that's 1,000. But I was nice enough not to include those. Powers of 4 you should know too. Yeah, 2 to the power of 4, that's 16. And then 3 to the power of 4, yeah, that's 81. Okay. Power of 5s, yeah, 2 to the power of 5, that's 32. 3 to the power of 5, that's 81 times 3, that's I think 243. Okay. And maybe for powers of 6, at least 2 to the power of 6, you should memorize that. That would be 64. Okay. So one of the key things we need to do before we start solving exponential equations by algebra is we need to know how to rewrite expressions using the same base. So I'm going to give you a whole bunch of samples here with 2 different expressions, and I want you to rewrite each expression so that the bases are the same. Okay? So I'm looking at 1a, and we've got a base of 2 and a base of 16. Well, this is where if you know, oh, 16, hey, that's 2 to the power of 4, then, hey, it's easy to change things into base 2. So in this case, I'm going to change into base 2. And the only reason I say that is because I know 16 equals to 2 to the power of 4. Which means the first one I don't need to change, 2 cubed, that's done. So for 16, I'm going to rewrite the 16 as 2 to the power of 4 first. And we still have that little square there too. Okay? And I hope you remember those rules, those exponential rules. When you have a power raised to the power, you can actually multiply the powers together, and that becomes to the power 8. So I'll just put on the side here the exponential rule. If I have x to the power of m, all raised to the power of n, that just becomes multiplication, right? Okay, let's do part B. So we've got 1/9 and we've got 81. So, what base can we change this into? Now, I think you might be thinking, hey, how about the base of 9? Sure, we can do that, because 1/9 is the same thing as 9 to the power of, oh yes, negative exponents are possible, so -1. And then 81, of course, is just 9 squared. So if we do that, then I'll have here 9 to the power of -1, all raised to the power of 3, and that just simplifies to 9 to the -3. And over here, we have here 9 squared, and that's raised to the power of -2. So that's the same thing as 9 to the power of -4. Okay? Same base. Now, some of you will be thinking, hey, wait a minute. 9 can also be changed into base 3 you're totally correct. So there's two possible solutions in this case. We can change into base 3. So 1/9 would be the same thing as 1 over 3 squared, which would be 3 to the power of, you guessed it, negative, so negative 2. And then 81 is the same thing as, I think, 3 to the power of 4. Look at the chart up above. And if you did this scenario, you'd have here now 3 to the negative 2 raised to the power of 3. That's the one on the left. And that would be 3 to the negative 6. The one on the right would become 3 to the power of 4 to the power of negative 2. And that would be 3 to the power of negative 8. And that works just fine as well. Okay. All right, I'm going to let you try part C and then D. Okay, you try. Roots. Oh man, all that stuff from grade 10. Remember roots? The root of x. That's the same thing as x to the power of 1/2. If I have the cube root of x, that's 1/3. And we generalize this to like the nth root of x, which was x to the power of 1 over n. Okay, that's stuff from grade 10. And then sometimes we did something even more funky where we had the nth root and then we raised x to the power. Okay, and that just became x to the power of m over n. Think flower power, those of you who had me in grade 10. Remember the idea of the fractional exponent is that the bottom number is the root, get it, the nth root, and the top number is the flower, or that means it's the power. So, don't know if that helps. If it does, great. If it doesn't, delete from your brain. Okay, so 16, 64, I think both of them can be written as base of 4. Okay, so 16, well, yeah, I guess 16 is 4 squared. Well, you know what? This one's pretty actually even easier if I just simplify the root part first, shouldn't I? That's just 4, so that's 4 cubed. And then the cube root of 64 is 4, that's 4 squared. Well, that was easy. Okay. Now, if you didn't want to do that, we could also change it into base 2. So I'll say or change into base 2. Now, before I even do that, I think what I'm going to do is rewrite all these as exponents first. So using the stuff I just did over here to help us out, that flower power jazz, root 16 to the power of 3 can be written as 16 to the power of, yes, 3, and it's the root. So the root is the index of 2, so 3/2. And then the 64 could be written as 64 to the power of, that's right, 2/3. So in this case, if I change into base 2, how are the numbers 16 and 64 written in base 2? Well, I think 16 is just 2 to the power of 4. So I'll make that replacement. Okay, that just simplifies to what? 4 times 3 over 2, that's just 2 to the power of 6. And if I were to use the 64, that's just 2 to the power of 6. So 2 to the power of 6 to the power of 2/3. 6 times 2 is 12. That would be 2 to the power of 4. Okay. So either base 4 or base 2, both are fine here. Okay. Part D, I think, well, 125, yeah, that's a key number in the powers of 5. That's 5 cubed. So this must be 5 to the power of negative 3. 25, of course, is just 5 squared. So let's go ahead and make the changes. 5 to the negative 3, all raised to the power of x plus 3. And this other one here would be 5 squared raised to the power of negative 2x. Okay, let's simplify. And remember, when we have exponent to exponent, we multiply them together. So for this one, the base is 5. We're going to multiply together, which means we're going to distribute. So that'll be negative 3x minus 9. Okay, distribute the negative 3 into the x plus 3 binomial. Oops, sorry, that's x minus 3 binomial. Yikes, 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 yikes. Getting tired here. X minus 3. Distribute negative 3x plus 9. There we go. And the one on the right, 2 times negative 2x is just negative 4x. Done! And there you have it. Same base. Life is good. Okay? This trick, or this idea is very important, because when we solve exponential equations algebraically, we need to actually change them and rewrite them with the same base first. Okay? That's our ultimate first goal. So 2 to the power of 3x minus 2 equals to 16 to the power of 2x plus 1. I hope you know that, hey, oh yeah, 16, that's equal to, oh yeah, 2 to the power of 4. So, oh yeah, let's make that switch. Okay? We'll keep 2 to the power of 3x minus 2, and we'll replace 16 with 2 to the power of 4. And don't forget, we raise this to the bracket, or the exponent, 2x plus 1. Okay? I think our next step should be to try to simplify there, so we'll distribute. That becomes 2 to the power 8x plus 4. This is nice now, because if I want you to solve for x, look what you've just created. On the left side is an exponent expression, on the right side is an exponent expression. The left side the base is 2, the right side the base is 2. So if the bases are the same, now we can just equate the exponents. So we don't have to worry about the base anymore. We'll just say, hey, since the bases are the same, the exponent part should also be the same. 3x minus 2 should be really equal to 8x plus 4. Well, now it's just regular algebra from grade 8. Life is now good again. We'll subtract 3x off of both sides. How about I subtract 4 off of both sides as well? So I get this. We'll solve for x. We'll just say x equals to negative 6 over 5. And that's it. Just like any other algebraic equation, you can always plug it back in and double check that your answer is right. But I know it is. Okay. This is the idea. Find the similar base, rewrite the exponentials in that base, simplify into one exponential expression on the left and one exponential expression on the right, then equate the exponents and solve. So, your turn. Okay? Try B on your own. If you choose the base of 6, I'm very proud of you. Now go ahead and substitute. Now simplify. Now equate the exponents. And just do some simple algebra to solve for x. Done. Want some more fun? Turn the page. Oh, a few more trickier ones, hey? Okay. Alright, let's do C first. C I think you can handle, because 1/25 and 25, well, I think we've done that before. The only weird thing here is that 5 that's in front of the 25. I'll show you how to do that in a moment, but let's just see what you can handle first. That's right, base is 5. Okay, now it's time to put in the bases. So here we go. 5 to the power of negative 3, all raised to the power of x minus 3. We've got a 5 by itself, so by itself means it's raised to the power of 1. I'm just going to put that there because I think it helps us later on. Then you have the 25, which becomes 5 squared to the power of negative 2x. Okay, we will now try to simplify. So 5 to the power of negative 3x plus 9. This equals to, now we'll just leave the 5 to the power of 1 as is. We'll simplify the next part. 2 times negative 2x is negative 4x. Okay. Now remember how I said we have to have one expression on the left and one expression on the right? Well, we've got the 1 on the left, but on the right I see two pieces. So what can we do here to try to combine them? Well, let's use some other exponential rules. Remember that rule of x to the power of a times x to the power of b? That means when you multiply, you add the exponents together. Well, it's the same thing here. If I want to keep the base as 5, I better add the exponents since it's multiplication. So 1 plus negative 4x, well, that's just negative 4x. So 1 minus 4x is what's simplified on the right-hand side. The left-hand side stays the same, so there's no change. And now, since there's one exponent expression on the left and one exponent expression on the right, we now just equate the exponents and solve. Or actually, equate the exponents or the powers, I'll say. Okay. Solve. So negative 3x plus 9 equals to 1 minus 4x. In this case, I'm going to add 4x to both sides. We get x plus 9 equals to 1. Would be nice if I actually were to, that's equal to 1. Move the 9 or negative 9 to the side, so x equals to, oh, what happened here? That's a plus sign. So that's not 10. What's happening here? Computer is lagging again. 8. Negative 8. Yeah, thanks. Okay, done. All right. D looks the nastiest of them all, but of course, we like nasty stuff here, so we'll do nasty stuff. What part looks the scariest of them all? If it's that 3 to the power x part, you are definitely correct. Here's a little trick we can do for this one. I'm going to ask you to make a substitution, so I'm going to use my favorite letter A. Let A be something that's really ugly. In this case, how about that 3 to the power of x? Okay. Now, if I let that equal to A, how is that going to help me with the other thing, 3 to the power of 2x? Well, note, 3 to the power of 2x, I can write as 3 to the power of x, all raised to the power of 2. Remember, multiplication, right? Two exponents back to back. Together, it's just multiplication. So I can just rearrange the order and say, I want 3 to the power of x all squared. And this helps immensely because now the first term here becomes a squared. The second term here becomes 10a. And oh yeah, this is a trinomial. Can you say factor? Say factor. I didn't hear you say factor. Say factor. Okay, so let's factor. Two numbers that multiply to positive 9 and add to negative 10. How about negative 9 and negative 1? And so when we solve this, we get a minus 9 equals to 0, or a equals to 9. When we solve this, we get a minus 1 equals to 0, or a equals to 1. And you think you're done? Let's go back and resubstitute. So what do we have? Resubstituting. We have here now 3 to the power x equals to 9. We have over here 3 to the power x equals to 1. Now remember, we're solving exponential functions, so how do we rewrite them with the same base. Well, 9 is the same thing as 3 squared, so in this case, that's pretty straightforward. X equals to 2. But for the other one, what exponent is equal to 1? Remember, anything to the power of 0 equals to 1. So why don't I choose the base of 3, since that's what I want, and therefore here x also equals to 0. Heh, tricky, hey? But nonetheless, doable. Okay. Well, what's the point of solving if we can't do a word problem? So let's do a word problem, and hopefully we can use it to solve. Radioactive radium, ooh, scary, has a half-life of, well, 1600 years. We'll die way before that. So this means after 1600 years, half of the original mass of radium-226 will have decayed. If you start with 0.3 milligrams of this radium, how many years will it take for the sample to decay to 0.009375 milligrams? So tiny, tiny amount, okay? Well, we're going to have to figure out an exponential equation first of all. Remember that y equals to, I guess we can use ac to the power of x over t, or if you like the one from the last section, y equals to a c b x minus h plus k. That's fine as well. It's up to you. Most of these word problems, however, though, the h and the k values are 0, so I kind of like the first one, but it's up to you. Okay. Let's see. We start off with 0.3 milligrams, so A must be 0.3. It's half-life, so C is a half. X is the time. We don't know in years, but we do know that the capital T is time it takes for one cycle of this to occur. That's 1600 years. And because we want to have, in the end, 0.009375 milligrams. That's my final amount. It goes on the left-hand side. Okay, so what do we do next? Probably want to divide by 0.3, okay? Because I want to see if I can isolate to get one exponent by itself without a number in front. Grab my trusty calculator. I'm going to do a 0.009375. Oops, forgot a 0. Divide that by 0.3. 0.03125 equals to 1/2 x to the power of 1600. Now, to solve this algebraically, I'm thinking I need the bases to be the same. So that 0.3125 must be 1/2 to the power of something. Okay. You can either use your calculator, change it to a fraction, or just kind of guess and test. I'm just going to use guessing and testing right now. 0.5 maybe to the power of, let's say, 6. Let's see what that is. Oh, that looks like, too much. So, okay, a little bit less maybe. Power of 4. Oh, that's way too less. So how about power of 5? I think I've got it. Oh yeah. So this is the same thing as 1/2 to the power of 5. 1/2 to the power of x over 1600. Since the bases are the same, we can now equate the powers or exponent. So 5 must equal to x over 1600. We'll times both sides by 1600. How about a whopping 8,000 years later? Both you and I will be long gone by then. But radium-226 will still be here. Oh, hey. Feeling good? All right. Turn the page, and sometimes you can't write all the terms using the same exponential base. So until we learn something called logarithms in Chapter 8, we're going to have to actually solve this using a graphical approach. So, graphical approach means we want to solve graphically, so that's why I have your graphing calculator. All you really need to do is split it up into y1 and y2, so that's 10 to the power of, and put a bracket around the exponents, please, okay? And do the same thing with the 50, so negative x plus 1. Gonna make this a little bit smaller so we can see it, okay? Back to your graphing calculator, bring it out. Let's just type in the equations then, okay? So 10 to the power of bracket x minus 1. Oh, I forgot the 0. Okay. Underneath, it's 50 raised to the power of bracket negative x plus 1. I'm going to ask you to, let's find some appropriate window coordinates. Not too really sure, so maybe just a standard one will be good. Let's go zoom standard for now. So there's my, so it's not too bad. Probably want to focus on this area here, so gonna maybe change my window so I can just focus in on the upper corner there. Don't need too much for the x, so how about no more negatives? Let's just go -2. Y's, I don't think I need anything below the x-axis. Let's change it to 0. That was probably too high. Let's change it to 5. Let's see if I can focus in better now. Let's graph. Oh, there's my growth. Here's my decay. Looking fine. I might add. So this was good. So -2 and 10. 0 and 5. Going to do a quick sketch. Here's my axes. Here are my two graphs. One that's going up, which is growth. That's the first one. And then one that's decay. That's the second one. I want to find the intersection points. So second calc, intersect. First curve, sure. Second curve, sure. Take a guess, sure. And lo and behold, 1, 1. So what's my solution? I'm only solving for x, so just quote the x value, x equals to 1. That's it. Okay? I'll let you try the next one, part B, on your own. Okay? Try it, please. It's the same thing. Now, some of you might want to clean up this equation. If you want to, you can divide both sides by 4 to get 12 equals to 1/2 to the power of 2x plus 1. That works, but if you don't want to do that, and you just want to leave it as is, then I just ask you to copy the left side for y1. And for the right side, y2, I'll just go 4 times and put brackets, 1 divided by 2, all raised to the power of 2x plus 1. Okay? That's what I'm going to ask you to do. I'm not going to sketch this out. You go try it out and come back for the answer. Look like this one's in the negatives. Change my window. How about -10? That's better. Let's use the intersect feature again. 1, 2, 3. -2.29. So there we go. X equals -2.29. draw your own graph here. By the way, if I give you a question like this on the test where you have to actually do it by graphing, then yes, you must draw in your graph. Okay? Don't be lazy like me right now. Alright, and we're going to do one more question. This time we're going to ask you to solve it using the graph, because I believe you cannot find the same base. Once again, one of these compound interest type of questions. So how long does it take for $1,000 to reach 2,500 in value if the interest rate is 8.25? And in this case, compounded monthly. If you don't remember that formula, go back and think about it, or go back to your section 7.1 notes. Something like the final amount equals to the principal 1 plus I over, I think it was n, raised to the power of nt. Remember, A is the final amount, so that's 2,500. P is the initial amount, which is 1,000. Your interest rate as a decimal is 0.0825, so 1 plus 0.0825. Because you're compounding monthly, I believe n equals to 12. I'm going to split up that 8.25% into 12 pieces. Because of that, you compound more often, so that's 12 times the t. And in this case, you're going to solve by graphing this one out. This one's kind of messy, so let's see if we can simplify a little bit first. Divide both sides by 1,000. So 2.5 is equal to, what's that nasty decimal? 1 plus 0.0825 divided by 12. Doesn't look good. Oh, not too bad, I guess. 1.006875. 1.006875 raised to the power of 12t. Okay. So, graphing calculator time. Let's see what you get. $2.5. 1.006875 raised to the power of, man, lag. 1.006875 to the power of bracket 12x, close bracket, not 2x, 12x, arg. 12x. Okay, so this is 2.5. Better change my window. The y value doesn't need to be that big at 80. Break it down to like 8. Let's see. There's my growth function. Oh. Well, do I see them intersect? Oh. Better change my window just to make sure they actually do intersect. Let's make x max a little bit more. Let's set it 20. Much better, I think. Find the intersection point. Okay. And by the way, you should be like sketching this graph too, but once again, I'm lazy. So you do it in your notes, and I'll look for them in your notes. All right, here we go. Okay, sketch own graph. But the answer for T was 11.14. Wow. So less than 12 years, I guess. Okay. Feel confident to try some questions on your own now? All right. We'll do that in class.